Hello everybody, let's have a look at this interesting problem from the start of the 2021 AMC, AMC 12A, and this is problem 7. So first we're going to talk about why the problem is difficult, and then we're going to talk about how to solve it. So when we want to find the least possible value of a function, there's a few different ways, but usually if it's got a squared in it, for example, if we just wanted to know what's the least possible value of this bit, then it would be quite straightforward. Okay? The least possible value that a square can take is 0. So then you would know that x, y minus 1 equals 0, and then you would know that x times y equals 1. All right, and then x and y would have to be reciprocals of each other. Okay, so that's the first one. So we know that if x and y would be reciprocals, then the first bit would be its lowest one. So we get x equals 1 over y. Now let's look at the second bit. Now, when would this be at its smallest value, its least possible value? Well, the square of anything, the least value it can take is 0. So what this means is that x would be equal to negative y. So it would be equal to its additive inverse. So now we've got this interesting competition. We're saying, okay, it's got to be somewhere between its multiplicative inverse and somewhere between its additive inverse. Now, if you really want to tackle these kind of problems in general, you need multivariable calculus, I believe. I don't think there's any shortcuts in general. You want to find the minimum of a two-valued function, a function that takes two inputs. You're going to need to use multivariable calculus. But in this case, there is a neat trick. Yeah, so that's why the problem is difficult, is because the minimum has got to be between two sort of more elementary minima. But it's not clear where that lies. Now, a lot of problems in the AMC and maths challenges in general require you to see a certain trick. So you don't want to jump in too fast into trying one approach. Now, whenever you see a binomial being squared, you should just be able to do that in your head without even writing it down and just thinking about the terms. Now, the moment I saw this, I saw that this term here would end up having a middle term negative 2xy. And then this one, I thought it would have a positive 2xy. These two immediately jumped out at me, and I saw that they cancelled. So I thought, okay, well, if they cancel, maybe we end up with something similar, so maybe it's worth doing. So you've got to keep your mind open, and then if you see something, that might simplify it. Okay, that's a possible approach. So let's do that. We're going to expand it out now. Let's switch to a slightly thicker pen. This is going to be equal to x squared y squared minus 2xy plus 1. And then x plus y squared, of course, is x squared plus 2xy plus y squared. If we add these two together, they're going to cancel. They're going to cancel out. That's why we did it in the first place. And what are we left with? Well, we're left with what looks like a bit of a mess. To be honest, it doesn't immediately look like this is a simpler function. But remember, we just want to know the minimum of this function. Now, the minimum of anything squared is just 0. So what's the smallest that x squared can be? Well, the smallest this can ever be is 0. The smallest this can ever be is 0. It would already be made 0 anyway, but the smallest this can be is 0, and the smallest that this can be is 0, and they're kind of independent of each other. Therefore, what's left is 1. So all of these other ones can independently be made 0, and we're just left with a 1. Therefore, the answer is 1. Let's just go over how we did that again. When you look for the expansion, you see that there's a potential for simplification. And you pursue it, you end up with a bunch of independent squared variables, in which case it's very easy to know their minimum point because it's 0 for the square of any real number. I hope you found that interesting. Don't forget to like, comment, and of course subscribe. I'll be trying to put these up once a week. Thank you very much.